Example 3 in this lecture deals with a disc here on the left, which is attached to an arm which is turning at the rate omega 0 about the vertical shaft. This rotation rate is a constant, and we are supposed to find the acceleration of the point B which is attached to the disc. Let's go ahead and call the ground as the body B0, and we will call the disc as the body B1. I am doing so as to align with the formula that we have just written down for rolling motion. So let us go ahead and also differentiate the point B0 which lies on the ground and the point B1 which lies on the disc. We will use the coordinate systems that have just appeared here on the left. The red coordinate system which is attached here, I have not drawn the point, this point, let me call it C. This is the ground fixed coordinate system. The pink coordinate system is attached to the arm and is centered at O, and the blue coordinate system is the body fixed coordinate system of the disc. I could have positioned the red coordinate system also at O, and I have not done so only because it would become very messy. So let's now begin with the velocity analysis. Our strategy, as always, is to find a point and write its motion in two different ways. We will focus on the point B1. I am being careful here. This is the point on the disc coincident with the contact point B. So let's go ahead and do that. So here on the right, I have repeated the figure on the left, and now let's start writing down the velocity of B in two different ways. So the first way is to write down the velocity of B1, the point B on the disc, from the perspective of the ground, which is I am calling the body B0. We will use the rolling condition number 1, which said that when the body B0 is stationary, in this case the ground is stationary, then the velocity B1, the point B on the disc, will equal the velocity of the point B on the ground, VB0, which, because the body B0 is stationary, it will be 0. So the rolling condition leads to the formula that VB1 is 0. Let's call this equation 1. The second way is to consider the point B1 from the point of view of the disc. I can then write that VB1 is equal to Vg plus omega of the disc, which is B1, cross R V1 with respect to G. So this is the formula which relates the velocities of 2 points B1 and G on the same rigid body. In this formula, I do not know Vg and I do not know omega B1, and that is 6 unknowns, and this is a vector equation which is only 3. So therefore I need more information, and for that I will again look at this figure more carefully. Point G is attached also to the arm. So I can also relate point G's motion to the point O, which is at the other end of the arm. And I do that because I know that velocity of O is 0 because it is on the fixed shaft. So I will use this condition to now write that Vg is equal to Vo plus omega arm cross Rgo. I can combine these two equations, this one and this one, to write that VB1 must be Vo plus omega arm cross Rgo plus omega B1 cross RB1 slash G. Let's call this equation 2. Thus we have written down the velocity of B1 in two different ways, equation 1 and equation 2, and we can equate these to get the unknowns in the problem. What are the unknowns? Let's quickly identify them. V0 is not an unknown, I know V0. Omega arm, do I know omega arm? Well, omega arm is the rotation rate of the BFCS E prime, which is attached to the arm, which we know is rotating at the angular velocity omega 0 along E3, because that is what has been given in the problem here on the left. if you are not following, you can quickly write down the various coordinate systems and the relationships between them. So E0 centered at C with EI is taken by the rotation about E3 by some angle omega 0 t to the coordinate system E prime centered at O and given by the unit vectors EI prime, which will then be rotated about E1 by some angle theta, which I don't know, and theta will be changing with time, but the rotation is about E1 to give me the coordinate system attached to the disk, which is E, G, EI. So this flow chart can help identify that omega arm must be associated with this rotation, and therefore it is simply omega 0 along E3. So let's write that down. Omega arm is omega 0 E3. Either way, the point is I know omega arm completely. R, G, O, it's a known vector. R B1G is also a known vector. Omega B1, which is the angular velocity of the disk, is not known. So this is the only unknown in the problem. That's 3 unknowns and 3 equations when we equate the 1 and 2, and that should solve the problem. So equating 1 and 2 gives us 0 is equal to omega arm cross RGO plus omega B1 cross RB1 with respect to G. We already have written down omega arm to be this. We can now write down RGO to be capital R along E1 prime, while RB1 with respect to G to be small r E3. I am not being too careful about which frame I am using to write down these vectors. That's because at the current moment all of these coordinate systems are aligned. I just have to be careful if I start differentiating things. So this equation I am going to call 3. I can simplify this equation by using omega arm to be this, RGO and RB1G to be these, and I will get the equation which I shall call equation 4. So you may feel that you have solved the problem because you have got an equation for omega B1. Those are 3 unknowns and there are 3 equations over here. But you have to be careful. This equation cannot give you components of omega B1 along E3 because E3 dot this equation is 0. Okay. So how should I go ahead and solve this problem? Well, you can always put in the components of omega B1 and solve this equation. I will, however, suggest the following. By looking at the flow chart that you have over here and the problem that is drawn, we can write down that omega B1 is actually omega of E with respect to E prime plus omega of E prime with respect to E0. And that gives us that this must be some unknown velocity omega 1 along E1, because if you are sitting in the pink frame, which is E prime, and looking at the blue frame, which is E, then you will see that the blue frame is rotating around E1 at the rate omega 1 plus, and this rate we have already discussed must be omega 0 E3. I will now take this formula and I will put it in here, and the only unknown is now omega 1. When I simplify, I will get minus omega 1 E2 should be equal to omega 0 R by R capital E2, because capital E3 cross small e3 is 0 at the current moment. Small e3 and capital E3 are aligned, and I get omega 1 must be minus omega 0 capital R by small r, so that the angular velocity of the disk omega b1, which is given by this expression over here on the right, is obtained as omega 0 along capital E3 minus omega 0 capital R by small r along E1 prime. I can write E1 prime or I can write small e1. E1 prime and E1 are always going to be aligned because we obtain the blue coordinate system by rotating the pink about E1 prime. Therefore, E1 and E1 prime are always aligned. So that concludes the velocity analysis. You may be wondering that the question was about finding the acceleration of the point on the disk which is in contact with the ground at this moment. Why are we doing the velocity analysis? So we did it because it is usually better to do the velocity analysis before the acceleration analysis. As part of the velocity analysis, we have obtained the angular velocity of the disk, and as you will see, even though some of us who don't have enough experience with solving such problems may not see immediately, but this information will be required in order to find the acceleration. If you do not do a velocity analysis and you directly jump to an acceleration analysis, you will suddenly find that you need some quantities which can only be obtained after you have done the velocity analysis. Okay, so both ways are fine. You can jump directly to acceleration analysis, realize that you need quantities which will be found by velocity analysis, come back and do it, or simply just do the velocity analysis, find all the unknowns which relate to the motion of the rigid body that you are investigating, and then go ahead for the acceleration analysis. Let's now move to the acceleration analysis. For the acceleration analysis, we need to find the acceleration of the point b1 in contact with the ground. We will relate the acceleration of b1 to the acceleration of g because both b1 and g are on the disk. We don't know the acceleration of g, so we will relate the acceleration of g to the acceleration of O because both O and G are on the arm. The acceleration of O we know to be 0 because it is on the shaft. It will turn out that this one way of writing the acceleration of B is enough, and we do not need to find a second way to write the acceleration of B. So as I mentioned, the acceleration of B1 is the acceleration of G plus omega B1 cross omega B1 cross r b1 with respect to g plus the angular acceleration of b1 cross r b1 with respect to g. Ag is related to the acceleration of O through a similar formula because both g and O are on the arm. We can now combine these two equations and we can write down that A b1 is equal to AO plus okay. Now it is a matter of deciding whether we know everything on the right side of this equation. Let's check. Do I know AO? Yes, I do know the acceleration of O because it is on the shaft and it is fixed, so this is 0. Do I know omega arm? Yes, I do. I just found it over here as part of the velocity analysis. This is known, that is known. The location of G with respect to is AO is known. What about alpha arm? Alpha arm is the rate of change of omega arm, which is the rate of change of omega 0 E3. That's what we found omega arm to be, and that is 0 because capital E3 is a fixed vector and omega 0 is given to be a constant. So alpha arm is known and is 0. Omega b1 we just found again as part of the velocity analysis. Here it is. As I had said, when doing the acceleration analysis, you may find that you do need quantities which can only be found by velocity analysis. Here they are. We need omega b1 and we can only have found it if we had done the velocity analysis earlier, which we have. RB1G again we know. So now it's a question of, do I know alpha b1? Well, how do I find the angular acceleration of the disk? I take the angular velocity of the disk and I differentiate it. What is the angular velocity of the disk? Here it is on the left. So let's write that down. So this is equal to d by dt of omega 0 capital E3 minus r E1 prime upon small r. You could make this small e1 also. The first term does not contribute anything, that goes away, and I will get minus r by small r omega 0 e1 prime dot. Well, what is the rate of change of the unit vector e1 prime? e1 prime here in our flow chart belongs to the E prime coordinate system, which is rotating with respect to the ground by the angular velocity omega 0 about E3. So therefore, E1 prime dot is omega of E prime with respect to E0 cross E1 prime, which is omega 0 E3 cross E1 prime, which at this moment E1 prime is along E capital E1, so that this becomes minus omega 0 capital E2. Putting this equation and this equation together, I will get that alpha B1 is equal to omega 0 square r upon small r capital E2. Okay. So now I have got this equation in which this was the unknown, which I have now found. So I can combine these two equations. Let me number them. So this is 5 and this is 6. So substitute 6 in 5, this in this, and use all the known terms. Substitute for omega r, substitute for omega b1, substitute for alpha b1, substitute for the vector r b1g, substitute for the vector rgo. When you do that, we get the answer which is shown here on the left. The acceleration of b1 is found to be omega 0 square r upon small r e3 minus e1. There are two terms here, and each one of these two terms can be understood in an intuitive way, which is kind of fun to do. So let's do that. Let's begin with the second term first, which is easier. The second term is minus omega 0 square r e1, and the form suggests centripetal acceleration due to rotation of omega 0 on a circle of radius r, which is kind of what is happening. This point B1 is moving in a circle of radius r at the rate omega 0 because it is attached to the disk, which is going around on a circle as it is attached to this arm. The second term over here can be written as omega 0 r whole square over r e3, which looks like v square over small r e3, and it reminds us of centripetal acceleration of a particle with speed v on a circle of radius small r. Here on the left you have a circle of radius small r. If you were to sit on g and look at b1, it would look like it has a speed omega 0 r, so that with respect to g the acceleration of b1 would be of the kind v square upon r, and it would be directed towards g, that is along e3. So these are the two components of AB1 which we have understood. It is easy to see that this answer for AB1 satisfies the rolling condition when B0 is fixed, which it is in our case, because AB1 dot t is the tangent vector along the contact path. The contact path will be a circle of radius capital R, so the tangent will be along E2. So therefore AB1 dot t will be the same as AB1 dot E2, which, as you can see from the formula here, there is no E2 component, so AB1 dot E2 is 0. So the rolling condition number 2 is satisfied. Please note that AB1 is not 0. So the velocity of B1 is 0, but the acceleration of B1 is not 0. So that finishes example 3. and also finishes with it rigid body kinematics. And just like this guy, I will also request you to be patient. The course's best may yet come.